Semiconductor.
A semiconductor is a material which has electrical conductivity between that of a conductor such as copper and that of an insulator such as glass. Semiconductors are the foundation of modern electronics, including transistors, solar cells, light-emitting diodes, quantum dots and digital and analog integrated circuits. The modern understanding of the properties of a semiconductor relies on quantum physics to explain the movement of electrons inside a lattice of atoms. The increasing understanding of semiconductor materials and fabrication processes has made possible continuing increases in the complexity and speed of semiconductor devices, an effect known as Moore's law. The conductivity of a semiconductor material increases with increasing temperature, behavior opposite to that of a metal. Semiconductors can display a range of useful properties such as passing current more easily in one direction than the other, variable resistance, and sensitivity to light or heat. Because the conductive properties of a semiconductor material can be modified by controlled addition of impurities or by the application of electrical fields or light, devices made with semiconductors are very useful for amplification of signals, switching, and energy conversion. Current conduction in a semiconductor occurs through the movement of free electrons and holes, collectively known as charge carriers. Adding impurity atoms to a semiconducting material, known as doping, greatly increases the number of charge carriers within it. When a doped semiconductor contains excess holes it is called p-type, and when it contains excess free electrons it is known as n-type. The semiconductor material used in devices is doped under highly controlled conditions to precisely control the location and concentration of p and n-type dopants. A single semiconductor crystal can have multiple p and n-type regions. The p-n junctions between these regions have many useful electronic properties. Some of the properties of semiconductor materials were observed throughout the mid-19th and first decades of the 20th century. Development of quantum physics in turn allowed the development of the transistor in 1948. Although some pure elements and many compounds display semiconductor properties, silicon, germanium, and compounds of gallium are the most widely used in electronic devices.
Materials.
A large number of elements and compounds have semiconducting properties, including certain pure elements are found in group 14 of the periodic table. The most commercially important of these elements are silicon and germanium. Silicon and germanium are used here effectively because they have 4 valence electrons in their outermost shell which gives them the ability to gain or lose electrons equally at the same time. Binary compounds, particularly between elements in groups 3 and V, such as gallium arsenide, groups 2 and 6, groups 4 and 6, and between different group 4 elements, for example silicon carbide, certain ternary compounds, oxides and alloys, organic semiconductors, made of organic compounds. Most common semiconducting materials are crystalline solids, but amorphous and liquid semiconductors are also known. These include hydrogenated amorphous silicon and mixtures of arsenic, selenium and tellurium in a variety of proportions. These compounds share with better-known semiconductors the properties of intermediate conductivity and a rapid variation of conductivity with temperature, as well as occasional negative resistance. Such disordered materials lack the rigid crystalline structure of conventional semiconductors such as silicon. They are generally used in thin film structures, which do not require material of higher electronic quality, being relatively insensitive to impurities and radiation damage.
Preparation of semiconductor materials.
Semiconductors with predictable, reliable electronic properties are necessary for mass production. The level of chemical purity needed is extremely high because the presence of impurities even in very small proportions can have large effects on the properties of the material. A high degree of crystalline perfection is also required, since faults in crystal structure, such as dislocations, twins, and stacking faults, interfere with the semiconducting properties of the material. Crystalline faults are a major cause of defective semiconductor devices. The larger the crystal, the more difficult it is to achieve the necessary perfection. Current mass production processes use crystal ingots between 100 and 300 mm, 4 and 10 in diameter, which are grown as cylinders and sliced into wafers. Because of the required level of chemical purity and the perfection of the crystal structure which are needed to make semiconductor devices, special methods have been developed to produce the initial semiconductor material. A technique for achieving high purity includes growing the crystal using the Czochralski process. An additional step that can be used to further increase purity is known as zone refining. In zone refining, part of a solid crystal is melted. The impurities tend to concentrate in the melted region, while the desired material recrystallizes, leaving the solid material more pure and with fewer crystalline faults. In manufacturing semiconductor devices involving heterojunctions between different semiconductor materials, it is often important to align the crystal lattices of the two materials by using epitaxial techniques. The lattice constant, which is the length of the repeating element of the crystal structure, is important for determining the compatibility of materials.
Physics of semiconductors. Energy bands and electrical conduction.
Semiconductors are defined by their unique electric conductive behavior, somewhere between that of a metal and an insulator. The differences between these materials can be understood in terms of the quantum states for electrons, each of which may contain 0 or 1 electron, by the Pauli exclusion principle. These states are associated with the electronic band structure of the material. Electrical conductivity arises due to the presence of electrons in states that are delocalized, extending through the material. However, in order to transport electrons, a state must be partially filled, containing an electron only part of the time. If the state is always occupied with an electron, then it is inert, blocking the passage of other electrons via that state. The energies of these quantum states are critical, since a state is partially filled only if its energy is near to the Fermi level. See Fermi-Dirac statistics. High conductivity in a material comes from it having many partially filled states and much state delocalization. Metals are good electrical conductors and have many partially filled states with energies near their Fermi level. Insulators, by contrast, have few partially filled states. Their Fermi levels sit within band gaps with few energy states to occupy. Importantly, an insulator can be made to conduct by increasing its temperature. Heating provides energy to promote some electrons across the band gap, inducing partially filled states in both the band of states beneath the band gap, valence band, and the band of states above the band gap, conduction band. An intrinsic semiconductor has a band gap that it is smaller than that of an insulator, and at room temperature significant numbers of electrons can be excited across the band gap. A pure semiconductor, however, is not very useful, as it is neither a very good insulator nor a very good conductor. However, one important feature of semiconductors, and some insulators, known as semi-insulators, is that their conductivity can be increased and controlled by doping with impurities and gating with electric fields. Doping and gating move either the conduction or valence band much closer to the Fermi level, and greatly increase the number of partially filled states. Some wider band gap semiconductor materials are sometimes referred to as semi-insulators. When undoped, these have electrical conductivity nearer to that of electrical insulators, however they can be doped, making them as useful as semiconductors. Semi-insulators find niche applications in microelectronics, such as substrates for HEMT. An example of a common semi-insulator is gallium arsenide. Some materials, such as titanium dioxide, can even be used as insulating materials for some applications, while being treated as wide-gap semiconductors for other applications.
Charge carriers, electrons and holes.
The partial filling of the states at the bottom of the conduction band can be understood as adding electrons to that band. The electrons do not stay indefinitely, due to the natural thermal recombination, but they can move around for some time. The actual concentration of electrons is typically very dilute, and so, unlike in metals, it is possible to think of the electrons in the conduction band of a semiconductor as a sort of classical ideal gas, where the electrons fly around freely without being subject to the Pauli exclusion principle. In most semiconductors the conduction bands have a parabolic dispersion relation, and so these electrons respond to forces, electric field, magnetic field, etc. much like they would in a vacuum, though with a different effective mass. Because the electrons behave like an ideal gas, one may also think about conduction in very simplistic terms such as the Drude model, and introduce concepts such as electron mobility. For partial filling at the top of the valence band, it is helpful to introduce the concept of an electron hole. Although the electrons in the valence band are always moving around, a completely full valence band is inert, not conducting any current. If an electron is taken out of the valence band, then the trajectory that the electron would normally have taken is now missing its charge. For the purposes of electric current, this combination of the full valence band, minus the electron, can be converted into a picture of a completely empty band containing a positively charged particle that moves in the same way as the electron. Combined with the negative effective mass of the electrons at the top of the valence band, we arrive at a picture of a positively charged particle that responds to electric and magnetic fields just as a normal positively charged particle would do in vacuum, again with some positive effective mass. This particle is called a hole, and the collection of holes in the valence can again be understood in simple classical terms, as with the electrons in the conduction band.
Carrier generation and recombination.
When ionizing radiation strikes a semiconductor, it may excite an electron out of its energy level and consequently leave a hole. This process is known as electron-hole pair generation. Electron-hole pairs are constantly generated from thermal energy as well, in the absence of any external energy source. Electron-hole pairs are also apt to recombine. Conservation of energy demands that these recombination events, in which an electron loses an amount of energy larger than the band gap, be accompanied by the emission of thermal energy, in the form of phonons, or radiation, in the form of photons. In some states, the generation and recombination of electron-hole pairs are in equipoise. The number of electron-hole pairs in the steady state at a given temperature is determined by quantum statistical mechanics. The precise quantum mechanical mechanisms of generation and recombination are governed by conservation of energy and conservation of momentum. As the probability that electrons and holes meet together is proportional to the product of their amounts, the product is in steady state nearly constant at a given temperature, providing that there is no significant electric field, which might flush carriers of both types, or move them from neighbor regions containing more of them to meet together, or externally driven pair generation. The product is a function of the temperature, as the probability of getting enough thermal energy to produce a pair increases with temperature, being approximately exp. e.g. kT, where K is Boltzmann's constant, T is absolute temperature and Eg is band gap. The probability of meeting is increased by carrier traps, impurities or dislocations which can trap an electron or hole and hold it until a pair is completed. Such carrier traps are sometimes purposely added to reduce the time needed to reach the steady state.
Doping.
The conductivity of semiconductors may easily be modified by introducing impurities into their crystal lattice. The process of adding controlled impurities to a semiconductor is known as doping. The amount of impurity, or dopant, added to an intrinsic, pure, semiconductor varies its level of conductivity. Doped semiconductors are referred to as extrinsic. By adding impurity to the pure semiconductors, the electrical conductivity may be varied by factors of thousands or millions. A 1 cm 3 specimen of a metal or semiconductor has of the order of 1022 atoms. In a metal, every atom donates at least one free electron for conduction, thus 1 cm 3 of metal contains on the order of 1022 free electrons, whereas a 1 cm 3 sample of pure germanium at 20 DeGC contains about 4.2 x 1022 atoms, but only 2.5 x 1013 free electrons and 2.5 x 1013 holes. The addition of 0.001% of arsenic, an impurity, donates an extra 1017 free electrons in the same volume, and the electrical conductivity is increased by a factor of 10,000. The materials chosen as suitable dopants depend on the atomic properties of both the dopant and the material to be doped. In general, dopants that produce the desired controlled changes are classified as either electron acceptors or donors. Semiconductors doped with donor impurities are called N-type, while those doped with acceptor impurities are known as P-type. The N and P-type designations indicate which charge carrier acts as the material's majority carrier. The opposite carrier is called the minority carrier, which exists due to thermal excitation at a much lower concentration compared to the majority carrier. For example, the pure semiconductor silicon has 4 valence electrons which bond each silicon atom to its neighbors. In silicon, the most common dopants are group 3 and group V elements. Group 3 elements all contain 3 valence electrons, causing them to function as acceptors when used to dope silicon. When an acceptor atom replaces a silicon atom in the crystal, a vacant state, an electron hole is created, which can move around the lattice and functions as a charge carrier. Group V elements have 5 valence electrons, which allows them to act as a donor. Substitution of these atoms for silicon creates an extra free electron. Therefore, a silicon crystal doped with boron creates a p-type semiconductor, whereas one doped with phosphorus results in an n-type material. During manufacture, dopants can be diffused into the semiconductor body by contact with gaseous compounds of the desired element, or ion implantation can be used to accurately position the doped regions.
Early history of semiconductors.
The history of the understanding of semiconductors begins with experiments on the electrical properties of materials. The properties of negative temperature coefficient of resistance, rectification, and light sensitivity were observed starting in the early 19th century. In 1833, Michael Faraday reported that the resistance of specimens of silver sulfide decreases when they are heated. This is contrary to the behavior of metallic substances such as copper. In 1839, A. E. Becquerel reported observation of a voltage between a solid and a liquid electrolyte when struck by light, the photovoltaic effect. In 1873, Willoughby Smith observed that selenium resistors exhibit decreasing resistance when light falls on them. In 1874, Carl Ferdinand Braun observed conduction and rectification in metallic sulfides, and Arthur Schuster found that a copper oxide layer on wires has rectification properties that ceases when the wires are cleaned. Adams and Day observed the photovoltaic effect in selenium in 1876. A unified explanation of these phenomena required a theory of solid-state physics which developed greatly in the first half of the 20th century. In 1878, Edwin Herbert Hall demonstrated the deflection of flowing charge carriers by an applied magnetic field, the Hall effect. The discovery of the electron by J. J. Thomson in 1897 prompted theories of electron-based conduction in solids. Carl Baedeker, by observing a Hall effect with the reverse sign to that in metals, theorized that copper iodide had positive charge carriers. Johann Königsberger classified solid materials as metals, insulators and variable conductors in 1914. Felix Bloch published a theory of the movement of electrons through atomic lattices in 1928. In 1930, B. Gudin stated that conductivity in semiconductors was due to minor concentrations of impurities. By 1931, the band theory of conduction had been established by Allen Harris Wilson and the concept of band gaps had been developed. Walter H. Schottky and Neville Francis Mott developed models of the potential barrier and of the characteristics of a metal semiconductor junction. By 1938, Boris Davidov had developed a theory of the copper oxide rectifier, identifying the effect of the p-n junction and the importance of minority carriers and surface states. Agreement between theoretical predictions, based on developing quantum mechanics, and experimental results was sometimes poor. This was later explained by John Bardeen as due to the extreme structure-sensitive behavior of semiconductors, whose properties change dramatically based on tiny amounts of impurities. Commercially pure materials of the 1920s containing varying proportions of trace contaminants produced differing experimental results. This spurred the development of improved material refining techniques, culminating in modern semiconductor refineries producing materials with parts per trillion purity. Devices using semiconductors were at first constructed based on empirical knowledge, before semiconductor theory provided a guide to construction of more capable and reliable devices. Alexander Graham Bell used the light-sensitive property of selenium to photophone transmit sound over a beam of light in 1880. A working solar cell, of low efficiency, was constructed by Charles Fritz in 1883 using a metal plate coated with selenium and a thin layer of gold. The device became commercially useful in photographic light meters in the 1930s. Point-contact microwave detector rectifiers made of lead sulfide were used by Jagadish Chandra Bose in 1904. The cat's whisker detector using natural galena or other materials became a common device in the development of radio. However, it was somewhat unpredictable in operation and required manual adjustment for best performance. In 1906 H. J. Round observed light emission when electric current passed through silicon carbide crystals, the principle behind the light-emitting diode. Oleg Alusev observed similar light emission in 1922 but at the time the effect had no practical use. Power rectifiers, using copper oxide and selenium, were developed in the 1920s and became commercially important as an alternative to vacuum tube rectifiers. In the years preceding World War II, infrared detection and communications devices prompted research into lead sulfide and lead selenide materials. These devices were used for detecting ships and aircraft, for infrared rangefinders, and for voice communication systems. The point-contact crystal detector became vital for microwave radio systems, since available vacuum tube devices could not serve as detectors above about 4,000 MHz. Advanced radar systems relied on the fast response of crystal detectors. Considerable research and development of silicon materials occurred during the war to develop detectors of consistent quality. Detector and power rectifiers could not amplify a signal. Many efforts were made to develop a solid-state amplifier, but these were unsuccessful because of limited theoretical understanding of semiconductor materials. In 1922 Oleg Alusev developed two-terminal, negative resistance amplifiers for radio. However, he perished in the Siege of Leningrad. In 1926 Julius Eggert Leinfeld patented a device resembling a modern field effect transistor, but it was not practical. R. Hill and A. W. Pohl in 1938 demonstrated a solid-state amplifier using a structure resembling the control grid of a vacuum tube. Although the device displayed power gain, it had a cutoff frequency of 1 cycle per second too low for any practical applications, but an effective application of the available theory. At Bell Labs, William Shockley and A. Holden started investigating solid-state amplifiers in 1938. The first p-n junction in silicon was observed by Russell Ohl about 1941, when a specimen was found to be light-sensitive, with a sharp boundary between p-type impurity at one end and n-type at the other. A slice cut from the specimen at the p-n boundary developed a voltage when exposed to light. In France, during the war, Herbert Matter had observed amplification between adjacent point contacts on a germanium base. After the war, Matter's group announced their transistron amplifier only shortly after Bell Labs announced the transistor